Okay, fluids and complexes. And always remember, if you're not part of the solution, you're part of the precipitate. So it's a good thing to remember in life.
Do you want to be a precipitator or not?
Well, precipitation, yeah, I don't know. It's a good question. Philosophically, we can come back to that one at the end. Okay, so what are we going to learn about today? We'll learn about what an ideal solution is. We'll learn about the relationship between concentration and activity, what the activity coefficient is, how do we determine the ionic strength of a solution and its influence on activity coefficients. And we'll learn about complexes and their importance in geochemistry. So some definitions to start with. So a liquid is a fundamental state of matter. Okay, so it has properties such as fluidity and the ability to conform to the shape of their container while maintaining a constant volume. And we know this empirically because we take a glass of water, it stays in the glass, but it fills the entire space below the air-water interface. So what's a solution? So a solution is a specific type of liquid where one substance, the solute, is completely dissolved into another substance, which we call the solvent, to form a uniform mixture. So the solvent is the medium into which the solute is dissolved.
So this only applies to ionic bonding, right?
Uh,
Ionic compounds. You keep covalent. Will covalent things
yeah,
dissolve?
they are sparingly soluble, but they will eventually go into solution to some extent. Yes.
Okay.
Yeah. So, for example, if we put a quartz crystal into a glass of water, it's not going to dissolve instantly, but given sufficient time, some of it will break down. Yeah.
But not
Okay.
much of it.
Not much. No. No, quartzes, but if we take olivine, olivine would dissolve more rapidly than quartz, but still slowly.
Yeah, what's interesting is, if you want to dissolve a lot of quartz in water, you only have to do one thing. You just have to heat up the water.
That's right.
And
That's right.
you can do that if you can keep it from turning to steam. But okay, keep going.
Yes. Which we
I
will.
don't think it has to
Well,
be ionic anyhow. I mean, pentane would be soluble in hexane.
Good
yeah.
point. Well,
Yeah.
yeah, I was thinking about water, but you're thinking about hydrocarbons. So interesting.
Yeah. Okay.
Yeah.
No, excellent. Good discussion. So then in this course, we want to think about mineralizing fluids because we're interested in metals forming ore deposits. And so a mineralizing fluid is one that's going to carry the metals that we're interested in getting into an ore deposit. And so mineralizing fluids can exist within a wide range of temperatures and pressures. And so we can think of a mineralizing fluid as being a magma. When we talk about magmatic nickel copper deposits, for example, which we'll talk about in subsequent lectures, down to very low temperature aqueous fluids. So, for example, some types of copper deposit have relatively low temperatures. And so I'm going to introduce just very quickly, because we're going to talk more about this next week. But we can think in terms of an ore deposit systems model. And the only reason I'm really mentioning it now is because we need to form hydrothermal fluids or solutions. In other words, we need to have water or magma carrying our metals from some source, which is in green. Then we have to transport it, say, through the crust, up to some trap environment. Okay, where in the trap environment is where we change, say, the redox conditions or how oxidizing and reducing it is, or the pH or both, and then deposit those metals in an accumulation which is economic. So when we talk about an ore deposit, we really are implying that it's an accumulation of metals which can be extracted economically. So the interesting thing about that is if we take the price of gold, which right now is around $3,500 an ounce, which is ridiculous. It's ridiculously high compared to just a decade ago. So lots of lots of gold deposits are now ore deposits. But if we drop the price of gold down to $1,000 an ounce, there's a lot of ore deposits which would no longer be ore deposits. They would just be deposits. Okay. So I'm going to introduce the concept of a phase diagram. So we have three phase diagrams. The details, the geometry is the same for all of them. And really, what a phase diagram is showing, in this case, it's a pressure or water depth within the ocean versus temperature diagram. And what we have here is a line, solid line, that goes from sea level. So we know that water boils at sea level at 100 degrees C, right? So as we go further and further into the ocean, the pressure increases, and this line represents the boundary between liquid water and water vapor, right? So we call that a phase boundary. And so what these symbols represent are hydrothermal vents on the seafloor. And what you see is that some of these hydrothermal vents just emit hot water. And this is really important because these hydrothermal fluids carry lots of metals and are forming deposits on the seafloor today. Right? Some of these symbols actually fall right on the phase boundary. And in that case, what happens is as the hydrothermal fluid exits from the seafloor, it can flash to steam, and then it recondenses once it reaches lower temperature. And so the image on the right there is a chimney, a hydrothermal chimney, which is composed of, in this case, it's mostly composed of iron sulfide minerals, iron oxide minerals, and silica. And what you see is these little, what look like feathers, right? And this is steam. So within the chimney, the hydrothermal fluid is in the liquid state. And as soon as it exits the chimney, it flashes to steam. And we know this chimney occurs at about 565 meters water depth. And when we probed it with a temperature probe, it came back as 271 degrees Celsius. But we actually know that the fluid temperature is 265 degrees Celsius because if we go to 500 meters water depth over here and come over here, it's actually one of these symbols right on the boiling curve. The diagram on the left is just showing where this is from a background. So behind a subduction zone. And this diagram will become much more obvious as we go through this course as to why it's important. So really interesting chimney, flashing to steam. Tom.
Sorry, Matt. I didn't quite understand where the 5-degree difference came from between.
Oh, yes, good point. So what that means is our temperature probe was not calibrated correctly. Because we know that it's going to flash to steam at that water depth. This phase boundary is the boundary between water and steam. And so because we know the water depth, we can calculate the temperature at which that would happen. So our temperature probe was just slightly out of calibration. Great question. So you see something on this diagram called CP. So that's called the critical point. So what's the critical point? Well, if
You
we
got
look
a
at
question?
Got
You
a
had
question from John?
John.
You may be getting to it anyhow, but I guess my question is, does it matter where the metal is deposited depending on the temperature? So if it's, super hot water coming out and it's not going to flash, it'll be deposited outside on the ocean floor and vice versa. If it's just the right temperature and it's going to flash immediately as a deposit right there and plug up the holes, or.
So that's an excellent question. And the flashing to steam doesn't really affect the deposition of the metals. It does affect how metals are transported. Some can go into the vapor phase and most stay in the liquid phase. What causes the precipitation is in most cases, is the fact that you've, say, got a 350 degree C fluid. So that would be down here, 350 degrees C, say A31 here. And it's then mixing with seawater at that depth. Seawaters have got an ambient temperature of about 2 degrees C. So we have this incredible temperature difference. And so metals that are soluble at high temperature are insoluble at low temperature. And so they'll precipitate out. Okay. And hopefully this will become a little more evident as we go through this lecture.
Yeah, it's important to remember, I think, that the solubility of anything in any fluid is increased with higher temperature. That's a general rule, isn't that?
There's a few exceptions to that. There's a few minerals that have what we call retrograde solubility. They actually become more insoluble as you increase temperature.
Oh.
And anhydrite is an example of that. So anhydrite is calcium sulfate.
Okay.
And it has retrograde solubility. Yeah.
Okay. So generally, but not exclusively.
Generally speaking, that's true. Yeah. Okay. So critical point. So here's another phase diagram. So we've got pressure and temperature, and we have our phase boundary between liquid and vapor, just as we saw it for the ocean floor. And this diagram shows several things. And so one of the things that it shows is what happens to the critical point as you go from pure water, which is here, to water with 10% salinity, sodium chloride, and 25% salinity. So 25% salinity we would call a brine. And we'll talk a little bit about brines in a minute. Just for comparison's sake, seawater has about 3.5 weight percent salinity. So seawater would be probably down in right about here. Okay. So that's the drive home message there, is that the critical point changes as the composition of the fluid changes. And so to go with a brine won't flash to steam or won't reach its critical point until much higher temperatures and much higher pressures compared to pure water. And so we can add this. So at the top, we have the phase boundary, a phase diagram again, but now showing ice, liquid water, and vapor. And we have a bubble here for supercritical fluids. The middle diagram is basically a density plot of water molecules. So in the vapor phase, water molecules are highly dispersed. In the pure liquid phase, they're highly concentrated. Past the critical point, it's sort of it's betwixt and between. Right? In the bottom plot, these are just isochores, which are basically densities. So in a vapor, water's not dense. It's a vapor phase. Pure water is dense. And as we get past the critical point, we vary to different densities as a function of where we are within that phase space. And this will become, I know it's a little complicated to understand, but I think this next video will, and let's hope it works, will explain what a critical fluid is.
So this is our supercritical fluid demonstration, and what we can see on screen here is we have a cell, and this is a sealed cell, and there's a camera pointing to the front of the window. So if I shake the table, we can see the liquid inside vibrating. So we have a liquid and we have a gas on top, and what we're going to do is we're going to heat it up. So if we flick the switch on the front of the demonstration, we're going to heat the cell up, and because it's a closed system, what we'll see on screen is we'll see the liquid start to boil. And as the temperature increases, the gas moves from the liquid to the vapor phase, and the density of the vapor phase increases and the liquid phase decreases until we reach a certain point when the two become indistinguishable from one another, and this is a supercritical fluid. So you'll have noticed that the dividing line between the liquid phase and the gas phase has now almost disappeared, and we've got a homogeneous mixture. So that's now our supercritical fluid. And then if we run the demonstration in reverse, so now we'll cool the cell down and we'll see the opposite thing happen. So when the temperature of the cell reaches approximately 45 degrees, we'll see this phase separation occurring, and we'll regenerate the liquid phase and the vapor phase. There we go. So you can see we get this fantastic snowstorm effect where the gas comes out of the solution and rises to the top, and we get droplets of the liquid forming, and these fall to the bottom. And if we shake the demonstration, you can see now we've reformed the meniscus, so the separation between the liquid and gas phases. And it takes a little bit of time for the liquid to completely get back to where it was at the beginning, so we can still see some liquid droplets forming at the side on the demonstration. One of the reasons we're interested in supercritical fluids is that we're trying to do something called supercritical fluid electrodeposition. So this will involve taking nanostructures, nanoporous materials, and using supercritical fluids to actually deposit materials at the bottom. So the reason we're using supercritical fluids is that they behave partly like a gas, but also like a solvent as well. So you can dissolve things in them, but importantly they flow like a gas, and also they have zero surface tension. So if we have very, very tiny nanoporous materials, to be able to get material into the bottom, we need something which will be able to travel right down to the bottom of the pore and has zero surface tension. And then we'll be able to deposit materials layer by layer and build up nanoscale electronic devices.
Helped you understand supercritical, or what happens at the critical point. We'll explain supercritical fluids. Is there any questions about that? No? Okay. Anyway, I like that video. Okay, so what's the difference between activity and concentration? So in an ideal solution, we could say that the activity of the solute, which we can give activity, the symbol A, is equal to the concentration. So what's an ideal solution? An ideal solution would be something with almost nothing in it. All right, so if we took one molecule of sodium chloride and dropped it into absolutely pure water, it would no longer be an ideal solution. All right, so we have this relationship then between activity and concentration. What that implies is if we add more and more stuff to our pure water, then the activity is no longer the same as the concentration. So concentration is what we would measure analytically. So if we take a volume of seawater and take it to a lab and say, tell me how much of stuff is in there, they would analyze that seawater and they would give us the concentration of sodium and the concentration of chloride. But actually, within that piece of that volume of seawater, not all the sodium is available for reaction, and not all the chloride is available for reaction. And so we can think of activity as the effective concentration. So how much of that sodium is not locked up in other molecules, but is available for reactions, right? And this is really important when we're forming hydrothermal fluids and forming ore deposits. Okay, so because solutions are non-ideal, especially with ionic species, they don't behave. Real solutions are non-ideal, sorry. And this is because of electrostatic interactions between charged ions, so van der Waals forces and hydrogen bonds and things like that. And ions are surrounded by regions of water molecules. And so if we take our chloride ion, it's negatively charged. And so what's going to happen is that the water molecules will orient themselves around that ion so that the hydrogen end, which is the more positive end, will be pointed towards the chloride. And equally for the sodium, the opposite would be true. The fact that water is polar means that the negatively charged oxygen end of the water molecules will orient themselves towards the positively charged sodium ion. All right, so the fact that we have these shells of water around our ions in solution in some ways impedes sodium and chloride from being involved in reactions. And as I'll talk about in a minute, the other reason activity doesn't equal concentration is because of the formation of complexes. And so what does this look like? So here's a plot where we have the concentration in moles, and I'll talk about what that means in a minute, of sodium hydroxide, right? And as we increase the strength of sodium hydroxide, the activity coefficient, and I should have explained what the activity coefficient is the activity coefficient is the constant, and maybe I have that. Yeah, so here we go. The activity coefficient is equal to this constant times the concentration. So for pure water or for pure sodium the solution with no sodium hydroxide in it, the activity coefficient would be 1 and activity would equal concentration. Okay, so the effective concentration would be the same as concentration. As we increase the salinity, we increase the ionic strength of sodium hydroxide, then we see that the activity coefficient decreases. And what that means is that as we increase salinity, more and more of the sodium and the hydroxide are surrounded by water molecules and therefore are not available for reaction. And so the activity coefficient goes down. So the effective concentration decreases. The other thing that we see on this diagram is that this changes as a function of temperature. So the activity coefficient is much lower at high temperature for a given concentration of sodium hydroxide than it is at low temperature. And so when we're thinking about hydrothermal fluids, say a nice seafloor vent might be venting at 300 degrees C, so that the effective concentration of things are much lower than their analytical concentration. Does that make sense?
No, but I'm halfway there.
Okay. So how can I explain it better?
Rephrase in terms of like, there once was a little sodium ion and
there once was a little sodium ion, and when we dropped it in water, right, it got surrounded by water molecules. And these water molecules impede it from being involved in reactions. So
it's like being surrounded by your own surrounded by a bunch of people or something that are keeping you from interacting with others. Got another question here.
Yep.
It was a comment to talk a little bit about the effect of temperature on activity coefficients.
Okay. So as we increase temperature within a given solution, the activity coefficient goes down, which means that because as we increase temperature, things are vibrating faster, they get pushed together more in solution, and so they're not as available for reaction. And actually, this will become more obvious as I talk about complexes. Okay? Yes, no?
Yeah, I think that explained it.
Okay.
Wait, sorry, one more quick question.
Sure.
So kind of thinking about this in terms of water activity, and maybe that's where I'm going wrong. Like you have pure water has water activity of 1, seawater has water activity of 0.98. Does that mean if you were to heat up seawater, its activity would also go down, or am I misunderstanding?
No, that's probably true. I don't know
Okay.
the specific answer to that question, but yes, I think that's right.
Okay,
Yeah.
thank you.
Yeah. Okay. we're running out of time. So ionic strength. So ionic strength is defined as this very simple equation. Ionic strength is 1/2 the sum of the concentration of elements in solution multiplied by their charge squared. So all that really is saying is that, sorry, the molar concentration, which again, I'll explain in a minute. All that's really saying is we sum up everything based on its charge, and that gives us the ionic strength. And we take 1/2 to account for the fact that we have cations and anions in solution. Okay. And the ionic strength of seawater is about 0.7. And as you said, activity of seawater is about 0.98. And that what this shows is, so we have a here. So we take magnesium chloride and we dissolve it in water. It's a salt of chloride, so it's highly soluble. We'll end up with magnesium 2+ and chlorine 1-. That'd be chloride because it's an ion. And we have 2, so for every mole of magnesium chloride, we end up with 1 mole of magnesium in solution and 2 moles of chloride in solution. So here's our equation, and we just say 1/2 of the sum of magnesium times 2 times that squared, charge squared. So the charge is 2. So we multiply that, the molar concentration of magnesium by its charge squared. Add that to the molar concentration of chloride times its charge squared. And we end up with that the ionic strength of that solution is 0.3 moles if we started with 0.1 moles of magnesium chloride. I hope that's not too confusing. Basically, it's a measure of how many ions in solution. And so if we think of ionic strength as the amount of stuff in solution in ionic form, we can think in terms of how much metal can we move around as a function of salinity. All right. And we're going to talk more about complexes in a minute, but right now I've got 4 plots that show the molar concentration of iron, molar concentration of zinc, molar concentration of manganese, and the molar concentration of lead, all metals that we find in ore deposits in abundance. Plot the molar concentration of chloride. And the red star represents seawater. And 1 molar iron would be 56 grams per kilogram, right? And that's based on what a mole is. And so what this diagram is showing, and this is for some real samples of brines, so very salty fluids, much more salty than seawater, that as we increase the salinity, we can move more metals in solution, right? And this is really important. So as we increase ionic strength, we can move more metals as complexes. And that's what we're going to talk about next. And so, yes, Clinton.
So is it a bad idea to use lead pipes for plumbing?
It's a very bad idea to use lead pipes for plumbing, particularly if you are drinking brine.
Brine's great.
It's good for keeping your kippers in, I guess, but okay, so what's a complex? So the difference in activity and concentration is partly due to the formation of complexes. And so if we have a solution that contains calcium and sulfate ions in solution, we can form a species calcium sulfate. Now the little 0 there means it's in solution. There is a mineral called anhydrite, which is calcium sulfate. And if it was the mineral, we'd put a little S beside the 4. So this is a complex in solution. And so because we can form this complex in solution, there's now effectively less calcium 2+ and less sulfate 2- for reactions, because some of it's locked up as a complex. Okay? And we can write that as what's called an equilibrium constant, which is basically a measure of how much of that complex are we going to form. So if we have an equation where we say calcium plus sulfate will give us this molecule in solution. So That means it's in solution, not a precipitate. And what we do is we write that stability constant is it represents how stable the complex is. And where does it go? There it is. And so we put the activity, so A is activity, the activity of that molecule divided by the activity of the ions. And so the more the reaction goes to the right, the higher that K value is. That's all it's really saying. And so there's two consequences of complex formation. The concentrations of the free calcium and sulfate in solution are reduced, so the effective concentration is reduced. And then the ionic strength of the solution is decreased because calcium sulfate is a neutral species. It's not an ion, so it's not going to contribute to ionic strength. So a complex can be thought of as a dissolved species formed from two or more simpler species, which all occur in solution. And we've already said that strength of the stability constant tells us how stable that complex is. And so for most trace metals and many major ions are transported in solution, in particular in hydrothermal fluids, as aqueous complexes. And that's why this is important. And just to reiterate, I said this earlier, but a ligand is an anion or neutral molecule that combines with a cation to form a complex. Okay, importance of complex. Complexes of dissolved species that also occur as a mineral tend to increase the solubility of that mineral. And all that that means is that if I'm forming calcium sulfate in solution, I can dissolve more anhydride, which is calcium sulfate solid. Okay. So that's what that says. And so most metals actually occur as complexes rather than their free ion. And so when we want to absorb things, so we can think of absorption as the association of a metal to a mineral surface, which is really important because that can attenuate metal migration in fluids if metals absorb to mineral surfaces. And their ability to absorb depends on how they're complexed. And also how toxic a metal is in the environment is also fundamentally related to its complexation. And this is a very fancy diagram, and details are not important at all. All this is showing is that if we look at the cation uranium, right? The cation uranium is complexed in different forms as a function of pH. And so all of these lines represent is the relative proportion. So we can see that at low pH, uranium is mostly complexed as UO2. At high pH, if we have carbonate around, so we have CO2 around, at high pH, most of the uranium is in a carbonate complex. And so the difference between an oxide complex and a carbonate complex affects how soluble uranium is and how far it can be migrated in a fluid, such as a hydrothermal fluid. And this affects how we make uranium deposits. And rapidly running out of time. So I'm going to introduce now, which we're going to talk about more next week. We introduce an EH-pH diagram. So all of the EH is measuring in millivolts on this plot is how oxidizing or reducing a solution is. So high EH values is highly oxidizing, low EH values are highly reducing. And what this diagram shows is different iron minerals as a function of changes in redox, or EH, and pH. And this is for some real waters. Some of these waters are oxidizing, and we see that the iron would precipitate. So PPD means precipitated. So when iron is in a solution with lots of oxygen around, it's not soluble. It precipitates out. And you see this when you leave your car out in salty winters for too long, you get rust, right? That's basically what that is. It's iron oxide. In reducing waters, iron can form 2+, and 2+ iron is highly soluble. So it can move around quite freely unless there's lots of reduced sulfur around, in which case we'll form pyrite, which is FeS2, iron sulfide. And why is this important? Well, Bob already showed a Gaussian profile or a supergene profile. This diagram is just a little more complex version of that. But basically what we have here, the blue dashed line is the water table. Below the water table, we have our primary sulfides. Above the water table, we have our oxide zone, which is our iron oxides, because iron's insoluble at high oxygen contents or very oxidizing conditions. And then we form these secondary minerals further down, which I mentioned earlier. We'll come back to this concept in later lectures. And so up here in this oxide zone, this is what we form, is these iron oxides. And this is commonly called a Gaussian. And so here's another EHPH diagram just showing that we can form these iron oxides or jarosites and iron sulfate at high oxygenated conditions and quite a range of pH values.
So if you took that diagram and put the red and the pink and the blue and the orange on there,
Yep.
The red
Okay.
would be on the lower.
The red would be in the pyrite.
Uh-huh.
The siderite is iron carbonate, so that would be the blue. Okay. And the iron oxides and sulfates would be the pink and the orange, depending on where you are, depending on the pH.
Yeah, thinking about Gaussian's relationship to sulfides really makes those diagrams come to life, I think. Because they're pretty abstract diagrams by themselves.
Yeah, they are. Okay, I think there's 2 slides left. Let me just check. Yes, 2 slides left. So complexes. So I just wanted to touch, because we're going to talk more about hydrothermal fluids, but I just wanted to touch on, and thinking back to that diagram with iron, lead, zinc, and manganese on it. So most metals form chloride complexes in high chloride solutions. So we move copper as copper chloride, zinc chloride, lead chloride, iron chloride, etc. Gold can move around as a chloride complex or as a bisulfide complex, that is hydrogen sulfide. And so all this diagram is showing is the different forms that different metals can take in solution, right, in hydrothermal fluids. And so this is really important for how we might precipitate things to form metal deposits. And I'll finish off with this diagram, which hopefully is not too confusing. So here we have temperature on the x-axis, and on the right-hand y-axis is basically the concentration of gold. At low temperatures, we can move gold as a sulfide complex, gold HS2 minus. Gold HS2 minus. At higher temperatures, we move gold as a chloride complex. As we lower temperature, gold chloride becomes less and less stable, so we can move less and less gold around. So all that means is as we lower temperature, we can form a gold deposit. So if we have a high temperature fluid carrying lots of gold around, and then we say mix it with a cold fluid, we would then lower the temperature and we would lose our gold out of solution.
So another way to think about this diagram is, wouldn't the gold deposit be there at the 350 degrees? Because that's the least solubility.
If you've got lots of sulfide around, it's gonna carry on as a bisulfide complex until you get even lower temperatures. Yeah.
So it's really, gold is where you find it. So another way to phrase that would be, gold is where you find gold depends on what was carrying it to where it was deposited.
Exactly. And then what happened at that trap site. So if we go back to, just scooch back here. One problem with animations, it's getting there, is getting back to this diagram, right? So we can move gold from its source along this blue arrow as a transport, as a chloride complex or a bisulfide complex. And at the trap, something changes the conditions. We lower the temperature, we change the redox state. Something happens to force that gold out of solution to form a gold deposit.
So this diagram, it's deceptively simple because this idea of the mineralization system comes from the petroleum systems, but when we think of traps, we mostly think of structural traps or stratigraphic traps. But with minerals, the traps could be EH, they could be pH, they could be anything that changes the solubility of the fluid, of that element in fluid. And that, I mean, coupled with the fact that we're dealing with 92 elements, that is the complexity of the ore deposit systems model. Is like,
exactly.
This has got 92 different dimensions.
Yeah, next week I've got a couple of different examples of different ways of expressing the ore deposit systems model, and then we'll go through some of the complexities of the different systems models for different styles of mineralization.
Yeah. No, I mean, that was a great lecture, and what I like about a lecture like that is if the students aren't confused, they weren't paying attention. So